Students, dear students, welcome to the first live session of the course Solar Energy Engineering and Technology. So before we address the issues concerning to this course, let us recapitulate some of the important aspects what we have covered so far in a PPT. I hope my screen is visible to you all. So our course is Solar Energy Engineering and Technology. And so far we have covered almost 4 modules. In module 1, we have introduced solar energy. Then in module 2, basically we have learned about solar radiation geometry. And in module 3, solar radiation estimation was elaborated. And in module 4, solar photovoltaic fundamentals and its application was introduced. So in lecture 1 of module 1, basically we have covered the energy scenario. We have defined need of energy, forms of energy, world energy scenario, then Indian energy scenario, global trend of generation of renewable power, trends of generation of solar power. In lecture 2 of module 1, we have introduced the overview of solar radiation conversion devices and its applications. Under this lecture, we have addressed different routes of exploiting solar energy, methods of energy utilization, devices for thermal collection and storage, working of solar PV generators, concept of solar power plants. Basically, in this lecture, we tried to give some of the important aspects and overall scenario of solar energy conversion and its application. In lecture 3 of module 1, we have learned the physics of propagation of solar radiation from sun to the Earth's surface. So how solar radiation is propagated. So for example, if solar radiation comes and strike on the Earth's surface, then how this solar radiation again bounce back to the Earth atmosphere? And what happens when solar radiation travels through the Earth atmosphere? All the phenomena were elaborated and atmospheric absorption scatterings were discussed. Sun-Earth relationships were discussed, and then what are different type of radiations like diffuse radiation, normal radiation, and then global radiation, which is nothing but the sum of diffuse and normal radiation. Also air mass, AM0. What is AM0? When we are talking about extraterrestrial radiation, then we will go for AM0. And when we are basically interested about testing of solar modules, then we will go for AM 1.5 spectrum. And in lecture 1 of module 2, we have basically covered solar radiation and sunshine measuring instruments, like what kind of instruments are used for measurement of different solar radiations. And also we have covered the concerns of solar equipment designer, then units of radiation, and then radiation data. What kind of radiation data we normally need for analysis, and what are the units we use for representing the solar radiation. In lecture 2 and 3 of module 2, basically we have discussed about solar radiation geometry, because this is very, very important, at what angle solar radiation comes, and then how we need to take a look at the situation about radiation consideration. And that's how we need to learn the different angles, like what is latitude, what is declination, what is hour angle, what is surface azimuth angle. All angles were studied very exhaustively. Then solar radiation geometry about horizontal and tilted surfaces. Then local apparent time. What is local apparent time? Why this local apparent time is important? Then solar path diagram, or you can say sun path diagram. These are all required while designing a solar devices very effectively. In lecture 1 of module 3, basically we have introduced the correlations and calculations of extraterrestrial radiation. So we have learned how solar radiations are calculated for a particular locations, and we have learned the different classes of radiation, how it is represented, hourly radiation, hourly average of daily radiations. So all those aspects were discussed, and we also understood really the need of the correlations. For example, the correlations developed for say states like, say for example, I'll give an example of a place, say California or USA. So same correlation cannot be applied in Indian context. Say for example, if we consider Madras. So this cannot be done. So we need to concern about our local atmosphere, and then we need to correlate our meteorological parameters with respect to the radiation parameter in order to find out the what is called radiation spectrum. Then classification of weather, then calculation of monthly average of daily extraterrestrial radiation, different correlations for estimation of monthly average of daily radiation. So these all are required. And see, why this kind of correlations are required? Why not a single correlations can solve all these problems? This is not actually no. Sometimes when you receive some kind of information, it might be in daily form, daily average radiation, but you are interested about the monthly average, or you might be interested about hourly average. So that's why we need specific correlations for estimation of radiations for a particular case. Under lecture 2 of module 3, we have primarily discussed about estimation of solar radiation. So different correlations were studied, and an estimation of hourly global beam diffuse radiation on horizontal surface and clear skies. So there are different conditions like clear skies and cloudy skies. So what happens when you are considering a case when solar radiation is not coming from the sun directly to the earth because of the cloud? And if there is no cloud, then what happens? Then how we need to modify our correlations for estimation of solar radiation received by particular locations in order to design a solar devices or utility system. And also we have learned the total radiation estimation of an inclined surface. And while discussing this, we have considered instantaneous cases, hourly. Instantaneous cases means in 1 hour time, the kind of deviation taking place that is considered. So we are assuming that in 1 hour time, things are not changing much. And then monthly average of daily, then hourly, and then monthly average of daily. So these all the aspects were considered and discussed. And finally, in order to strengthen the understanding, we have considered some of the numerical examples, and this has been solved. In lecture 1 of module 4, basically we have covered solar PV conversion and importance of PV conversions and challenges, construction of PV cells. So working principles, the band gap loss mechanism. This is just an overall of solar PV conversion. Then we have studied semiconductor physics, like classification of semiconductors, doping, Fermi energy level, PN junction, drift current, diffusion current, generations of solar cell materials. All those aspects were elaborated very precisely. And also we have given emphasis on performance characterizations or characteristics of PV cells, like how to generate IV characteristics curve, and what is a simplified, what is called our diagram that represents solar characteristics and solar cells. And also we have derived the estimation of maximum power of the solar cells. So of course we can use devices to know the amount of power generated by solar cells, but we can take help of mathematics to solve the maximum amount of power to be delivered by solar cell. An effect of variation of solar insolation and temperature on the characteristics of solar cells, and then solar cell efficiency and band gap energy. In lecture 4 of module 4, solar modules, arrays, and PV systems were considered. Because you see, first we're interested about cells characterization, then we'll go for bigger version like arrays, then from that we'll go for modules, then arrays. So that way we have done all those analysis, and we have studied the classification of PV modules, the effect of shadowing, backing factor, module efficiency, ways of maximization of PV module, then MPPT, and then what are different possible strategies for operation of MPPT, PV arrays, then PV systems. So all the components were covered under this lecture. So far we have covered this many modules. I think module 4 is in progress, and next other components will come, like PV systems. What will happen to the off-grid system? What will happen to the grid-connected system? What is the battery system? So all those things will come in the coming lectures. So thank you very much for your attention. So I would like to discuss some of the queries received during the discussion forum. So I have picked one. I think most of the things were responded by our teaching assistants as well as myself. And here there is a confusion, like Swanson's law. What is Swanson's law? They are very much spectacular to know, and how does this works. So this is something like, if it is very difficult to understand, I can give you one example. Say, for example, if I consider, say, this is one axis and this is one axis. This may be your x-axis, and which represents maybe your cumulative volume or cumulative module shipments. And the vertical axis we can consider is the cost. So if I consider, say, any value, arbitrarily I can choose any values. Say, for example, I'll write one vertical line here, and this may be 1,000. I'll write 1,000 here. Write 1,000. 1,000, okay? It's a shipment, it's a megawatt or maybe kilowatt, any value you can write. And say, for example, here we have, say, 100 rupees per watt. Okay, I'm not going into this figure, what is represented or what is shown in the slide. Just I'd like to give one example. Say, in this quantity, when it is manufactured, it costs was say 100 rupees per watt, then if we multiply by 2, then it will be say 2000. Okay, so this will be 2000. So when this 2000 production volume achieved, then it is decreases by 20%. 20% of the cost. That means rupees 80 per watt. So that way we can come to this point and we can connect it. And further, if you're interested to know, see this condition, just 2000 multiplied by 2, this is the 4000, right? Any point you can consider here 4000. So when this 4000 amount is manufactured, then another condition, this 80% of 20%, so it is 16, no 16 rupees. So 80 minus 16, it will be 64, right? So this will be like 64. So this will be rupees 64. So as this production goes on increasing, this price of the solar modules actually not decreasing. So that's what is observed by Swanson's, and this is quite effective, and we can consider this is one of the rule of thumb. This is going to happen. So for example, if I say now, if you are interested to buy a computer, you need a computer having very good configuration, like it has to be very fast, okay, response, I should say, but cost you want that lower, okay. So what you want, like you want a very high configured machine at lower cost, okay. So this can be connect to these kind of laws, because this is going to happen, okay. So you don't have time to wait, so you want to complete it as soon as possible, and you want to pay less. Okay? So that's what it is saying in this law. And yeah, this is the primary observations I got. And one more queries I got in the discussion forum. That student Simran Tyagi, he was saying that in MOOC assignment, I don't know which assignment he is talking about. When I solved the question number 10, I was getting the answer 1500. So maybe I'll respond to these queries through discussion forum, because I don't know exactly which assignment you are talking about. And now, if you have any queries, we can discuss. And you can type it here, and I can respond. Yes, I can tell about MPPT. So MPPT is nothing but maximum power point tracking. See, I'll just share one more time my slide. So here, so this is I, this is V, right? And our IV characteristics look something like this. And if we draw VP diagram, so just this will be somewhat like this, and it will meet somewhere here. Okay, So this is your IV, and if I write this axis is your P, and this is your PV characteristics. Okay. So here at this point, dP by dV is 0, right? So this point is nothing but your maximum power point at which dP by dV is 0, right? So if we are operating the system at this point, you are maximizing the power condition irrespective of any solar radiation. So we are considering at any I here, this may be I1, and if we consider I2 here, maybe I1 is lesser than I2, or I2 is greater than I1, then under the condition, what will happen? This will be something like this, okay? And your this will be something like this, right? So every time when your I is sensing, that is solar insolation, which is represented by watt per meter square, is sensing, then what will happen? Your values will change, but no, the system will operate at maximum power point. So this power point, this will not come down to other point. So that means you are maximizing the energy absorption, which is required. And this MPPT is an electrical system. Okay, this is attached with an inverter nowadays. So inverter actually controls everything, and then it will ask the system to operate at maximum power point, so that you can maximize the power what is no generated in the system, and that can be used, right? And there are different algorithm used for running the system, so we are not going into that electrical system, but what you should know, like, no, our intention is to operate at maximum power point, right? And there are different strategies how to operate it. And again, we can edit, no, sometimes say for example, if you are interested to connect a load which is giving the MPPT voltage or MPPT power, then it's fine. You are maximizing with respect to the load which is connected. But sometimes if you have a system, but your load is lesser than the what is called PMPPT, then under the condition you are losing the power which is available for utilization. Okay, so always our attempt is to operate at MPPT point. That's why this kind of development has taken place. So you have a question like which solar cell is having highest efficiency commercially available. So see, now this multi-junction solar cells are available. So they are having very high efficiency. Sometimes it is 46% efficiency, it is reported. I'm talking about cell efficiency, not the module efficiency, right? So it's a multi-junction solar cells. But when you are saying like our most of the solar cells which is available in the commercial market is silicon-based solar cell. It is multi-crystalline solar cells are quite popular, and in if you consider the total market, then 90% of the solar cells are silicon-based solar cells. So in this case, no module efficiency is about 15-16%. Okay. Solar cell efficiency is also quite good, but not that like the way people are making for multi-junction solar cells. Other solar cells are also developed, but these are very costly. And nowadays, no perovskite solar cells are picked up, but there are some issues like stability and other. So if we could solve, then maybe this could be one of the best solar cells, which is very less cost. So if you have any questions. So your question is something like, can you please tell me about the software used for optimizing the solar cell PV? There are many softwares, but no solar cell. Normally, see, we can do some experiment, theoretical study, but no one will believe your theoretical study. So we need experimental observations mostly. So system level, you can use it. Like we have, say, a PV system or maybe pollution. These are the very good or effective softwares. You can use it for making solar PV power plant and solar thermal power plant. At least you can take help of those softwares for designing. But solar cell, no, I think we should not take a risk of designing the solar cell. Uh, but no, of course we can get some kind of knowledge, like know what are different layers formed one by one to make a solar cells. So that way you can do. But no one will believe you about software use in solar cell design. And of course, coding is available. You can do coding once you know all those parameters, like what is the conductivities and all. Like for example, if you work on solar photovoltaic thermal modules, then what are different layers, and then how resistance is offered by the different layers. Um, and when you model, maybe mathematical model or maybe MATLAB, if you solve, then you can get to know like how they are influencing the performance of a solar cell. So you can also know think of utilizing software like MATLAB. So this question, no, like you are MTech student and to get research assistantship in RA position means no RA position normally get after completing PhD. Uh, but project engineer and all you can apply. So it is a common advertisement, and it is available in the website of IIT Guwahati. And you can browse it and you can see it. And based on your eligibility, you can apply. So that's the procedure we normally follow. So if you please ask questions if you have any, otherwise you can discuss in the discussion forum. I hope that you are enjoying this course, because this course is like comprehensive. We have covered almost all the aspects of solar energy conversion, starting from need, and then different instrument use, then solar thermal, solar photovoltaics, and then we have concentrators under solar thermal, and then when we are talking about PV, then we have all decentralized system, standalone system, and then grid connected system. Also, we have discussed something about PVD systems and storage requirement. So it seems it is comprehensive. So you may ask questions, otherwise we will conclude the session in 5 minutes. Yes, Prasadji, you can use phase change material in building integrated solar PV. In fact, we are doing one work. One of my PhD students is already done some work, and then now we are going to make one small housing and going to implement this phase change material. And we have developed some kind of bricks as well. So we are doing it, and I'm hoping that we'll get very good result out of it. But of course, this can be used. So thank you very much for attending this live session, and hope you are enjoying all the lectures, and this will be very much helpful in your future studies, as well as if you want to do some kind of work on solar. So thank you very much for attending this live session. See you in the second live session. Thank you.
Thank you, sir.